Yes, so I'm a professor here in the Centre for Research in Biosciences at the University of the West of England in Bristol. Our main specialisms, or my main specialisms, are working in the sectors of agri-food, of health technologies, environment and water. And we spend a lot of our time researching and developing technologies with the general aim of improving people's lives. That's working particularly with small, medium enterprises and technology providers to translate those solutions from the lab into the real world. So it's my firm belief that there are lots of ideas, there's lots of sort of research that really stays inside filing cabinets, stays on laboratory benches, stays inside people's brains. What we really are interested in is moving those ideas and those solutions out of the place that you see here, like a laboratory, and out into the real world. The real world to help people, to provide solutions, because the world has lots and lots of challenges. You know, those challenges range from needing better sanitation and hygiene, needing improved food security, and needing improved water security. And our focus and emphasis is taking those grand challenges head on and seeing if we, in partnership with others, can help to make the world essentially a better place. Okay, so I've been working in the field of electrochemically activated solutions for probably over 25 years. I guess some of my main expertise is in that area, as well as applying those types of technologies to water disinfection, to the decontamination of surfaces, application to medical devices, and generally exploring the nature of antimicrobial substances or biocides, seeing how they interact with bacteria that may cause us harm or be a challenge to us in a range of settings. That could be in a healthcare setting, it could even be in the home, or it could be in a glass of water that you're drinking and ensuring that that water is bacteria free. And we spent a lot of time investigating at a very profound and deep level the mechanisms that give rise to some of those antimicrobial properties that you observe in many biocides, electrochemically activated solutions being one of them. And our research ranges from research across the UK, actually also out into other countries. So we work a lot in India. We've also done a lot of work in Europe with many other academic and scientific partners. So I guess we know a lot about electrochemical activated solutions. So we, I think, have been pretty instrumental in building up the scientific evidence that helps to describe, you know, in a way that people can understand, the antimicrobial efficacy, or if you like, the usefulness of using electrochemical activated solutions as an effective disinfectant. So over probably 3 decades, we've compiled, conducted, assembled a body of scientific evidence that's been published quite widely in peer-reviewed journals and scientific articles to really put forward the case that electrochemically activated solutions really does present an alternative to other disinfection products. So what is electrochemical activation? And in fact, this is nothing new. I mean, we've been drinking here in the UK water which has been treated with chlorine for well over 100 years. And in fact, that's probably one of the biggest, largest single public health interventions in the 20th century. So electrochemical activation has been used extensively in the water industry for producing chlorine which we use to dose mains water supplies, and that makes our water supplies nice and safe. What we've done with electrochemically activated solutions is adopt that technology. Obviously we're using better materials, we're using better technology to compartmentalize that in a way that can be used in the home or in the workplace. And electrochemical activation works by passing a very weak salt solution through 2 electrodes. And those 2 electrodes, albeit made of quite complicated surface materials, which provides a lot of the necessary science and reactions to give rise to that antimicrobial solution, those electrodes essentially help produce the solutions that are so effective. And this is quite a well understood and well known property called electrochemical cells. So essentially all the solutions that are produced, which we call electrochemical activated solutions, are produced in these electrochemical cells, and they're a little bit like batteries. What is unique about some of these systems are the materials by which these electrodes are made, and also the electrolytes that are used. So in many systems, the materials often are made of a whole range of elements and metals, which could be rubidium oxide, titanium oxide coated surfaces, and an electrolyte solution, which is essentially sodium chloride, a weak brine solution, is passed through these two electrodes. Those two electrodes have a potential applied to them, and that energy that's inputted into the electrochemical cell then kickstarts a whole range of reactions that occurs at the surface of the electrodes and between the electrolyte that passes through those electrodes. So many people would say, well, so what? Well, what happens in that cell is you get a lot of chemistry, and you get the formation of a lot of chemicals and radicals and sort of excited ions that give rise to antimicrobial properties. So for instance, what produces the disinfection in relation to bleach? Well, we know that is chlorine, but actually it's not just chlorine, it's the reaction that chlorine has in the water, and the resulting products, chlorine related products, provide that kill. In electrochemical technology, you for sure have chlorine products, but you also have other products related to water, so a lot of OH minus products. And essentially you end up with what I would like to call or term a little soup of reactive ingredients that really want to attack organic material, in our case bacteria, because they need to. Chemically and physically, they need to react. So we're creating a whole soup of excited reactant products, and those products are really useful. The nature of those products is such that they are can really only react with bacteria, and they can interfere with the membrane wall, and that interference in the membrane wall results in the death of the bacteria. Now, of course, this is happening at a very small level. In our world, we're applying that on big surfaces, we're applying that maybe even on food or in water. But the net result is the same. You get the interaction of your antimicrobial or your disinfectant with the bacteria, and that causes a disruption in the cell membrane, and that ultimately kills the bacteria. And in the research that we've done, this is universal. So all bacteria are subject to this interference when you apply electrochemically activated solutions to the bacteria. And this is nothing outstanding in that sense. It is a very common mechanism by which many disinfectants work. And this is how ECAs works. The work that we've performed, we've tested a range of disinfectants against a whole plethora of bacteria. Now, you can imagine how many bacteria are known to humans. I mean, they run into the hundreds of thousands, potentially millions of different types of bacteria that are out there. We've tested against all the kind of the ones that generally raise concerns. So these could be things like MRSA, they could be E. coli, they could be spores that you find, so C. difficile spores, and the results always the same. It's familiar. We get substantial kill. And a lot of biocides and disinfectants, they're measured against very unified and standard tests. And these are called EN tests, and they are European-wide. And in fact, they have similar tests in the States and similar tests in other parts of the world. And ECAS operates no differently than other accredited or plausible disinfectants. So they kill a whole range of organisms. And one of the questions I get a lot when I'm working with partners in particular is, well, does it kill X and does it kill Y? In reality, no biocide has been tested against all bacteria because that just doesn't make sense. From a scientific perspective, what we usually do is we take what we call gold standards, and those gold standards are usually types of organisms that are really difficult to reduce or kill. And we know that through the work that's been done in the past. So many organisms that are very difficult to kill include things like spores. So a lot of the gold standard tests that are undertaken are against a range of spore-like organisms, which are known to be really, really resilient to chemical attack. Yeah, or disinfectant attack, principally because they're sort of round balls with very hard walls, so it makes them very difficult to be penetrated by the disinfectant that you're interested in. And certainly in the work that we've done, and again this is out in the scientific literature, we've shown that electrochemically activated solutions provide a substantial log reduction in terms of kill of such organisms. In some instances better than perhaps products that the general public would be more familiar with, so things like bleach. And the nature of the biocide that we're dealing with, electrochemically activated solutions, all of these very excited products that are in this suit, all really, really keen and eager to react with something, means that one advantage of using electrochemically activated solutions is the speed of kill. So we've tested a whole range of organisms with very similar results, but one remarkable thing that emerges from this is the speed of kill. So that is the difference really between ECAs type disinfectants and more conventional disinfectants like alcohol, Virkon, which is a disinfectant we use in the laboratory, or indeed household bleach, is that the speed of reaction or the speed of kill is really, really fast. How fast? Well, we've done some tests on that, and these are not sort of conventional tests, so we don't usually do kinetic testing of microbials or antimicrobials, because that's not a kind of a standard way of assessing disinfectants, but certainly in the techniques that we've used, we've shown and demonstrated, and again this is out in the scientific literature, that the speed of kill arises within the first 2 seconds. So that's within 2 seconds of being in contact with a bacteria on a surface or in suspension, you get some mode of action. And that represents significant advantages in areas where there is a requirement of time, yeah, where you don't have the time to leave something for 10 seconds or 20 seconds or 30 seconds, or you need very rapid disinfection. Then electrochemically activated solutions provide, I believe, a good alternative. So how do we investigate kill kinetics? Well, that's actually really quite difficult, because if you have a fast acting biocide and you've only got 2 seconds, that requires a certain type of approach, scientific approach, which is not easily reproduced in many, many laboratories. In our laboratory, we use something called bioluminescence. And bioluminescence, most people will be familiar with fireflies, glowing things, glowing algae perhaps in the sea. Well, that is the nature of bioluminescence. What we're able to do is to take those inspirations from nature, so we harness those DNA abilities of those organisms, and we can transplant them into bacteria of interest. So for instance, we can do that with E. coli or Salmonella. What does this mean? This means, sort of cutting out a long-winded scientific explanation, is that when the bacteria is alive and well, or when it's metabolizing, it kicks out bioluminescence or light. Now that's really useful for us, and it's useful because we can detect light. So our hypothesis using these bioluminescent reporter bacteria is that if the lights are on and we can detect that light, that means that the bacteria is alive. If the lights go out, that's a really good indication that the bacteria is either dead or metabolically inactive. And if you think about it from a disinfection point of view, that's really what we're after. We're after either killing the bacteria or making the bacteria such that it cannot reproduce, or that it's not very, very active. The second advantage of using bioluminescence is not just that it reports or tells us something about the living organism that we're applying the disinfectant to, but also we can visualize that activity over space and over time. And that provides us with a really powerful tool for visualizing the disinfecting or decontamination event. So in experiments that we've performed, we've transformed bacteria into bioluminescent entities, so they're kicking out light, and we've applied our disinfectant. And what that's enabled us to do is to model and calculate how fast these bacteria are killed when applied with a disinfectant such as electrochemically activated solutions. And in some of the work, we've shown that this kill is incredibly fast. That in itself is very, very interesting because it elucidates two things. One, it gives you, if you like, a very quantitative measure on how these disinfectants are effective in relation to contact time. So in many industries where cleaning is imperative or decontamination is imperative, contact time of the disinfectant and the thing that you're trying to decontaminate is imperative. It's imperative from a hygiene and health perspective, but it's also imperative perhaps from a business perspective because time equals money. So if you understand that process very well, you can model your cleaning regimes or decontamination regimes to fit a suitable model that is appropriate for your particular setting or business. For me as a scientist, an even more interesting aspect of using bioluminescing reporter bacteria is this idea of regrowth. Now this is incredibly important. So we may think we've disinfected a surface or killed a bacteria, but in reality, and you see this on many products, in reality we maybe have disinfected 99.9%. Now in most people's books, that's a pretty good hit rate. When you're dealing with 1 trillion bacteria, that 0.1% still represents a significant number. And if there's one thing we know about bacteria, and most mums and dads will tell you this who have children, is that bacteria multiplies and grows. So one interesting aspect for us in modelling or understanding disinfection is what does that look like? What does that regrowth look like? So if you think you've disinfected a surface, how do you know that that bacteria is not going to come back 24 hours later? And this is incredibly important in places like hospitals or intensive care units because what we know about bacteria is they're pretty smart and they're some of the oldest living things ever to have been around on planet Earth. So they're adaptive to their environments and they're really smart things. So what we're trying to understand is if we apply different types of disinfectants, how does that play out in terms of the regrowth of the bacteria that we're trying to kill? And what we're able to do with bioluminescence is to demonstrate this very visually. So I explained earlier about bacteria glowing and being alive. Well, what we can do with our experiments or in our facility is treat those bioluminescent bacteria with a disinfectant such as electrochemically activated solutions, and we can actually visually watch the lights go out, which would imply that the bacteria is either metabolically inactive or hopefully dead. What's even more interesting is that we can keep our low light cameras that detect this bioluminescence rolling. So what usefulness is that? Well, that means that we can come back the following day and see if the bacteria that we think we've disinfected has grown back. And in some of the work we've done, it's pretty apparent that many disinfectants do not have a residual quality about them or do not kill enough bacteria in the initial application, and that results in regrowth. What we've discovered with using ECAs is that regrowth is very, very minimal. And if you look at some of the data that we've shown, you can see that glowing bacteria materializes for some disinfectants and some controls, but when ECAS is applied, that regrowth is virtually nil. And that's really what we're after, because ultimately it's sustainable long-term hygiene that we're after, as opposed to fighting this perpetual regrowth and rebirth of bacteria. Electrochemically activated solutions represent a new type of disinfectant in many ways. And we've been involved in this for many, many decades. And the attraction of this in the way that we produce these solutions and in the way that we apply them means that we can use this type of approach in many different sectors. So some of the sectors that we've been involved in include the food sector. Many people shop, they buy food, they take it home, they put it in the fridge, and particularly if you're like me, you're incredibly disappointed if the lettuce that you've bought then spoils in a very quick time. We've done work with other partners and in the food sector to demonstrably show that if you apply electrochemical activated solutions in a very sophisticated way on fresh produce, that you can extend the shelf life of that. And that can have profound implications across that whole sector, particularly through the supply chain. So if you can get an extra day, an extra 2 days, you can really change the way that we deal in food, and we can really reduce the food. And what I say a lot to my students in an opening lecture is, if we can extend the shelf life of a cherry tomato by 1 day, we can change the world. And in fact, that's actually what we've done. We've managed to show that by applying this type of technology to fresh produce, number one, it's safe to the consumer. Number two, it doesn't detract from the taste or the smell of the produce. Number three, the produce looks healthier because we're creating an environment in which that produce can thrive. It's not subjected to bacterial attack. I mean, bacteria want to run everything. They want to overtake the world, and quite rightly so. Why wouldn't you? What we need as human beings is food that is appropriate and fit for purpose. So we need good bacteria, and we need to maintain that. But we also need to minimize bacteria that make things more difficult, whether it's health or whether it's food. And what we've shown in some of the work we've done in the food sector is that we can extend the shelf life of many different types of fresh produce. There's always a need to decontaminate, and there's always a need to control biological agents in the workplace. Another example is in water. So again, using electrochemically activated solutions, we've shown that you can disinfect water to the same standards that the water companies or that the water supply to your house can be disinfected. So this approach is now an approved method for disinfecting waters, as endorsed by the Drinking Water Inspectorate, which has overarch control over the technologies that are fit for purpose for disinfecting water supplies. There's also a need of this, of course, in the general cleaning industry. So in our works, homes, offices, workspaces, there is a need for general sanitation and hygiene. And we've worked with companies throughout the UK to establish the use of this disinfectant for its application in those spaces. And that's being done now. So this product, this product exists, it's available, this scientific innovation exists and is available. What really needs to happen is its adoption and its widespread use. And at the end of the day, electrochemical activated solutions is a solution. It's water-based. It's very safe to humans. We handle it in our lab, my students handle it. We've been doing so for 20, 30 years. All the evidence tells us that's the case. You can do interesting things with it. So you can apply it as a mist, or you can aerosolize it for application in large areas. You can freeze it, and it maintains its efficacy. So freezing, you can imagine preserving fish or frozen products. So its application is quite widespread, and its application can be quite varied because it's a water-based solution. One of the attractive features of applying or utilising electrochemical activated solutions is its low environmental burden. And what do I mean by that? Well, the technology essentially is a device of various sizes, but the inputs required to produce the disinfectants that are so useful in many of these sectors is water and salt. There's no other chemical needed. You need energy and electricity, and that can be supplied by renewable forms if needed, but essentially that's all you need. In more conventional disinfectants, so things like household bleach, those products are produced in large chemical factories. They're boxed in plastic containers. They're shipped out and widely distributed. All that is at a cost. And many people really, I suppose, end their relationship with their bleach or household bleach once they've finished the empty plastic bottle. But of course, the story doesn't stop there. That bottle has to be disposed of, has to be transported, and has ultimately an environmental impact. And to put some of the plastic waste into perspective, in the UK alone, just in relation to drinking water bottles, we consume over 7 billion plastic bottles per year. That's not taking into account any other kind of plastic. And of course, disinfectants contained in plastic bottles contributes on top of that. So there is an imperative, I think, in this day and age to reduce our impact on the environment through carbon footprint, through energy, and through the production of chemicals, and more importantly, through the disposal of the materials that are used in part to supply the disinfectants that we heavily rely on. Electrochemically activated solutions can be produced in situ. So if you have a device like this, it can be wall mounted, and all you need is water and salt. And what you get out is a disinfectant that you can use. So even from a common sense perspective, that reduces the resource burden almost overnight. So if everybody in Western Europe adopted this approach, that would have a significant reduction in the amount of plastics and energy and chemicals that we're using and ultimately disposing, some of which are finding their way into the environment at levels that are just simply not sustainable. Electrochemically activated solutions provides us with an opportunity to change that. It's a small step, but I think it's a significant one, and I think it's one that we are compelled in many ways to undertake, principally because the science is there and the technology is there. What we need is behaviour change. I believe we all have a responsibility to drive change for the good. We need to live, and we need to leave behind a more sustainable world, a world that's fit for purpose for our children and our children's children. And you know, you talk about that, and many people now see that as a very corny thing. Well, I completely refute that totally. I'm very passionate about trying to leave the world as best as we possibly can in a better state than we found it. And we're not doing a very good job. No matter where you look, there is lots of pressures, and there is lots of doom and gloom. And that's because the numbers just don't add up. You know, I mean, any scientist will tell you this. You know, we are under a lot of pressure. But it is not in our nature to just throw everything down and walk away. We have to work towards providing sustainable, greener solutions. And that means that individuals, corporations, and governments have to take the lead on this. And particularly here in the UK, we have a very strong science and innovation base. We have a very innovative, I believe, in my experience, businesses, and we can lead the way. You know, we don't have to wait for permission. You know, what are we waiting for? You know, so my challenge to governments, my challenge to corporations, and my challenge to individuals is to change, is to adopt innovative green solutions and turn those solutions into normal. We all together should be embracing those greener technologies, because in turn they will create better solutions and improved solutions down the line. And I hope whoever's watching this decides whether it's electrochemically activated solutions, whether it's just something which improves you know, the world even in the most smallest way. I hope they do embrace those changes.